March 1943, Tunisia, North Africa. The Sherman lurched forward across the wadi and stopped, its engine idling while the turrets scanned left across the ridgeline. Then the impact. A German 88mm round punched straight through the driver's hood, right where the two armour plates met at their welded seam. The joint split open like paper. The shell detonated inside, and flames erupted from the hatch within seconds. 2 crew members made it out. 3 didn't. 50 yards back, in a forward depot surrounded by damaged tanks waiting for attention, Staff Sergeant Ben Harlow lowered his binoculars slowly. His jaw was tight. He'd seen this before. Last week, last month, over and over. Always the same weak point, always the same result. The problem wasn't the crew, wasn't the tactics, wasn't even the German gun. It was the seam. A structural flaw everyone knew about, but no one had fixed. Harlow turned back to his workbench, to the steel plates he'd been cutting for weeks, to the weld patterns he'd been sketching in his notebook. He knew exactly how to stop this. One simple addition, one welded plate. But the work order sitting on his bench said wait. Ben Harlow wasn't supposed to be a welder. He'd grown up in Scranton, Pennsylvania, working in his uncle's machine shop. When the draft came in 1941, the Army sent him to ordnance school at Aberdeen Proving Ground. 6 weeks learning to weld armour plate and sign off on repairs that could mean the difference between a tank rolling out or a crew burning inside one. By early 1943, he was a staff sergeant leading a 3-man team in a forward depot. Eddie Kovacs, the fitter, Jimmy Priest, who ran the cutting torch, and Harlow himself, who did the critical welds. They worked in tents and salvaged buildings, patching holes and replacing final drives. Their job was simple: send damaged Shermans back to the line. Fast, because the tanks kept coming back, and they kept coming back hit in the same places. The M4 Sherman's armour was sound, good steel, properly treated, but the early production models had a glacis made from multiple plates. The front slope was a 3-piece assembly, upper glacis, and 2 smaller plates forming the hoods over the driver and assistant driver positions. Those hoods were killing crews. They sat at the wrong angle, thinner than the main glacis, joined to the upper hull with seams that created stress points and shot traps. An 88mm round didn't need to penetrate. It just had to hit the seam hard enough to crack the weld, peel the plate back, or send spalling fragments into the crew compartment below. Hood hit, weld fails, driver dies. Harlow had seen it 12 times in 2 months. The crews knew the problem as well as he did. They piled sandbags on the glasses, welded spare track links across the hoods, bolted on scrap plates with whatever hardware they could scrounge. Some of it helped, most of it didn't. The weight threw off the suspension. The track links rattled loose. The sandbags turned to dust. And the seams kept failing. Engineers back at Aberdeen were working on a redesign, a large hatch hull that would eliminate the driver's hoods entirely, replacing the multi-piece glacis with a single cast section. Better geometry, fewer joints, no weak seams. It was coming, just not fast enough. In the meantime, tanks kept rolling out with the same vulnerabilities, and the work orders kept saying the same thing. Do not modify production hulls. Do not alter approved geometry. Wait for the redesign. Harlow understood the reasoning. You don't want field welders changing tank structure without engineering approval. You don't want chaos, 30 depots doing 30 different fixes, compromising ballistic integrity, creating maintenance nightmares. But understanding the reasoning didn't make it right, because the 80s weren't waiting, and the crews weren't either. So Harlow started documenting which holes got hit where, which seams failed first, which crew-applied fixes actually worked, and which were just wishful thinking. He talked to every tank commander who brought a damaged Sherman into the depot, asked what they'd seen, what helped, what didn't. One captain, a man named Briggs, whose tank had been hit 3 times in 4 weeks, put it plainly: "The hood seams are a death sentence. The right side of the turret's too thin. And if you take a round through the sponson over the ammo racks, you don't get time to bail out." Harlow wrote it down. Then he walked to the corner of the depot where scrap steel was stacked. Plates from knocked-out German tanks. Surplus from repair jobs. Steel that could be cut to size, beveled and welded directly over the weak points. The work order said, "Wait for the redesign." The crews said they didn't have time to wait, and Harlow had already watched 3 men burn because a seam wasn't strong enough. He picked up a piece of 1/2-inch plate, felt the weight of it, looked back at the smoking Sherman on the ridgeline. The next hit will come where the steel is weakest. April 1943. The pattern was becoming impossible to ignore. Sherman number 3/17 came in with a cracked hood seam, repaired according to specification, sent back out. 3 days later, it returned with the same seam split wider. The driver had taken shrapnel to the shoulder. Sherman 3A-22, hit on the right turret cheek where the armour thinned to accommodate the gun mantlet. The round didn't penetrate, but the impact cracked welds along the turret ring. Loader suffered a concussion from the shock. Sherman 3A-31, penetration through the left sponson, directly over the ammunition storage racks. The tank cooked off before the crew could bail. 4 men dead, more hits, and the same weak points, and the same casualty reports. Harlow wasn't the only one noticing. Across North Africa and Sicily, ordnance crews were seeing identical damage patterns. The small hatch Shermans, the M4 and M4A1, variants rolling off production lines in late 1942 and early 1943, all shared the same vulnerabilities. The driver and co-driver hoods were the worst. The geometry was wrong from the start. 2 separate plates, each bolted and welded to the upper glacis at shallow angles that invited deflection shots straight into the seams. When a German gunner couldn't penetrate the glacis directly, he aimed for the hood line. Let the weld do the work for him. The right turret cheek was almost as bad. To accommodate the gun's recoil mechanism, the armour there stepped down from 3 inches to just over 2 inches. A weak point any experienced panzer crew knew to exploit, and the sponsons, the hull sides above the tracks where ammunition was stored, were only 1.5 inches thick. A single penetration there could detonate the entire ready rack. Tank crews weren't waiting for Aberdeen to fix it. They were improvising in the field. Some welded spare bogey wheels to the glacis. Some stacked spare track links across the hoods and wired them in place. Some bolted sections of captured German armour over the sponsons. A few enterprising crews even poured concrete into wooden forms and let it cure directly onto the hull. The results were mixed. The added weight helped. Mass-absorbed impact even if it didn't stop penetration. But it also stressed suspensions, slowed the tanks and made them nose-heavy. And none of it addressed the root problem. The seams were still there, the shot traps were still there, and the hits kept finding them. Harlow watched a crew weld track links onto their Sherman one morning. The commander, a lieutenant named Briggs, saw him watching and shrugged. "I know it's not pretty." "It's not effective either," Harlow said. "First solid hit and those links are gone." "You got a better idea?" Harlow didn't answer immediately, because he did have a better idea. He'd been sketching it in his notebook for 2 weeks. Applique plates, properly beveled, welded at the hood seams, the turret cheek, the sponson sides. Not decoration, not improvisation. Actual armour reinforcement done right, but he also had that work order: do not modify production hulls. Briggs lit a cigarette and looked at his tank. "We go back out tomorrow, if we get hit in the same spot again." He didn't finish the sentence. Harlow looked at the Sherman, at the crude track-link armor, at the seams still visible underneath, at the crew depending on steel that wasn't strong enough. He thought about the stack of plates in his shop, about the welding rods, about the fact that he knew exactly where to reinforce and exactly how to do it. The work order said, wait. The casualty report said now. If the drawing won't change today, the tank will. April 22nd, 1943, 0600 hours. Harlow didn't ask permission. He just started cutting. Eddie Kovac marked the plates while Jimmy Priest fired up the cutting torch. They pulled 6 pieces of half-inch steel from the scrap pile, German armour from a knocked-out Panzer IV, irony not lost on any of them. First priority, the driver's hoods. Harlow measured the seam where hood met glacis. The crack line was always the same, a neat split right along the weld where the thinner hood plate joined the upper hull. He cut 2 rectangular plates, each sized to overlap the seam by 3 inches on either side. Then he beveled the edges. This wasn't field-expedient track-link welding. This was structural reinforcement that had to survive combat without cracking, warping, or pulling the base metal out of shape. The bevel created a groove that would fill with weld, bonding the applique plate to the hull across the entire contact surface. Not a tack job, a fusion joint. Kovac fit the first plate over the left hood seam, checked it with a square, tapped it flush. Gaps consistent, no high spots. Tack it, Harlow said. Kovac ran 4 small welds at the corners, just enough to hold the plate in position. Harlow inspected each tack, then nodded. Now came the critical part. Welding thick armor plate isn't like welding thin sheet metal. The mass absorbs heat differently. If you run the bead too hot, you burn through. Too cold, you get incomplete fusion and trapped slag. And if you don't control the cooling, the thermal stress warps everything. Harlow preheated the joint with a rosebud torch, brought the steel up to 400 degrees, not glowing, just hot enough to slow the cooling rate and prevent brittle welds. Then he struck the arc. The first pass was the root. He ran a narrow bead along the beveled edge, watching the puddle, listening to the crackle, feeling the feedback through the electrode holder. The slag curled up black and smooth. Good penetration, no porosity. He let it cool for 2 minutes, chipped the slag, inspected the bead with a flashlight. Clean. Second pass. Fill. He overlapped the root bead, building up the weld in layers, staggering his stops and starts to avoid weak points where one pass ended and the next began. The smell of flux hung thick in the tent. Sparks cascaded onto the dirt floor. The Sherman's hull ticked and pinged as the metal expanded and contracted. Third pass. Chapter. Harlow ran the final bead smooth, blending the weld into the base metal, creating a continuous surface with no sharp transitions to catch a shell's deflection. He set down the electrode holder, grabbed a chipping hammer, tapped away the remaining slag. The weld rang true under the hammer, no hollow sound, no flex. Kovac ran a piece of chalk along the seam, then wiped it clean. No chalk dust caught in cracks. The joint was solid. Harlow moved to the right hood. Same process. Measure, cut, bevel, fit, preheat, weld inspect. By 1400 hours, both hood plates were on. Next, the right turret cheek. This plate had to curve slightly to match the turret's shape. Priest heated the steel with the rosebud, and Kovac bent it over a section of pipe until the radius matched. Harlow test fit it against the thin section of armour. Perfect. He welded it on. Root pass, fill passes, cap pass. Last, the sponsons. These plates covered the ammunition racks along the hull sides. Harlow left a 1/4 inch gap between the applique and the base armour. early spaced armor effect, though nobody called it that yet. If a round hit the outer plate, the gap would disrupt the penetrator before it reached the main hull. By 1800 hours, the work was done. 6 applique plates, 47 feet of weld bead, 12 hours of labour. The Sherman sat on its jack stands, scarred and scorched and covered in fresh welds that hadn't been polished or painted. Not pretty, strong. Lieutenant Briggs walked into the tent, looked at his tank, and went quiet. "Will it hold?" he finally asked. Harlow tapped one of the hood plates with his hammer. Better than what was there before. By first light, the weak lines were weld lines. The test came 3 days later. Lieutenant Briggs took his reinforced Sherman out on a sweep near Kasserine. Harlow didn't go. He stayed in the depot, welding applique plates onto another tank while he waited. The waiting was worse than the work. If the welds failed, if the added plates cracked loose or warped the hull or created new stress points, he'd have made things worse. And 3 men would pay for his mistake with their lives. The Sherman returned at 1600 hours. Harlow heard it before he saw it. The familiar clatter of tracks, the diesel growl, the squeaking bogies. He walked out of the tent and watched Briggs's tank roll into the depot area. There was a fresh gouge across the left driver's hood. Deep, angry. The kind of scar that meant a German round had hit hard and deflected. But the applique plate was still there, still welded solid, and the seam underneath was intact. Briggs climbed out of the commander's hatch. His face was streaked with dirt and powder residue, but he was grinning. 88 hit us outside Gafsa, same spot that cracked the seam last month. He slapped the hood plate. This time the damn thing bounced. Harlow walked over and inspected the impact point. The weld hadn't cracked. The plate hadn't shifted. The gouge was deep enough that he could fit his fingers into it, but the base armor beneath was untouched. "Driver?" Harlow asked. Walked away. Didn't even get a headache. Word spread fast after that. By the next morning, 4 tank commanders were standing outside Harlow's tent, asking if he could do the same thing to their Shermans. By the afternoon, it was 8. By evening, Harlow's captain, a logistics officer named Drummond, showed up wanting an explanation. Harlow showed him the work order, showed him the reinforced Sherman, showed him the impact gouge that should have killed a driver but didn't. Drummond read the work order, looked at the tank, looked back at Harlow. "How long does it take?" 12 hours per tank, give or take. "How many can you do in a week?" "With my crew?" 4, maybe 5 if we skip sleep. Drummond nodded slowly. "Do as many as you can. I'll handle the paperwork." Harlow and his crew went to work. They developed a rhythm, a sequence, a process that turned improvisation into procedure. First, inspection. Identify which hull variant, which weak points, which seams had already started cracking. Second, layout. Measure the plates. Mark the cut lines. Kovac had an eye for it now. He could look at a hood seam and know exactly how big the applique needed to be. Third, cutting. Priest ran the torch. The German scrap pile shrank steadily as they cut plate after plate. Fourth, beveling. Grind the edges at 30 degrees. Create the groove for the weld. Fifth, fit up. Position the plate. Check it square. Check it flush. Tack the corners. Sixth, preheat. Rosebud torch to 400 degrees. Let the heat soak in. Control the cooling. Seventh, welding. Root pass first. Fill passes second. Cap pass last. Stagger the beads. Watch the puddle. Listen to the arc. Eighth, inspection. Chip the slag. Chalk test for cracks. Hammer test for voids. If it doesn't ring true, cut it out and start over. They worked 18-hour days. Slept on cots in the corner of the tent. Ate cold rations while the steel preheated. The acetylene bottles ran dry and they requisitioned more. The welding rods ran out and they borrowed from another depot. 1 tank, then 2, then 5. The hood plates became standard. Then they added turret cheek plates, then sponson plates over the ammunition racks. Other depots started asking questions. How thick? What bevel angle? What preheat temperature? Harlow wrote it down, sent copies to the Ordnance headquarters. By mid-May, 3 other maintenance companies in North Africa were welding applique armour using Harlow's methods. By June, it was a dozen. And then, on June 14, 1943, the paperwork caught up. Field Service Modification Work Order G104-W57. Official authorization for applique armour plates on M4 series tanks. Hood reinforcement. Turret cheek reinforcement. Sponson reinforcement. Everything Harlow had been doing for 2 months. The work order that said wait was replaced by a work order that said proceed. What began as unauthorized field repair became official US Army doctrine. Summer 1943. Sicily. The 3rd Armoured Division landed with reinforced Shermans. Not all of them, production couldn't keep pace with demand, but enough that the difference was measurable. The crews noticed immediately. A Sherman took a hit near Gala. The round struck the right hood seam at a shallow angle, exactly the kind of hit that had been killing drivers since Tunisia. The applique plate caught it. The weld held. The driver felt the impact through his seat but kept driving. Another Sherman caught an 88 on the turret cheek outside Palermo, the thin section that used to crack under pressure. This time the added plate absorbed enough energy that the base armour stayed intact. The crew stayed in the fight, tank after tank, hit after hit. The reinforcements weren't invincible. Nothing stopped a direct penetration from a German long-barrel 75 at close range. But the applique plates were doing exactly what Harlow intended. They were eliminating the easy kills. The shots that used to find seams now found solid steel. The weak points were still weak, but they weren't fatal anymore. The survival rate climbed. Ordnance officers started compiling data. Tanks with applique armour were returning from combat at higher rates than unreinforced variants. Crew casualties in hood-reinforced Shermans dropped by nearly 40%. Turret cheek reinforcements cut loader injuries in half. The numbers were undeniable, and the requests kept coming. By August, depot crews across the Mediterranean theatre were welding applique plates as standard practice. Supply sergeants requisitioned steel specifically for armour reinforcement. Maintenance companies that had never done structural welding were learning Harlow's techniques from copied instructions. Field Service Modification Work Order G104-W57 became one of the most widely implemented armour modifications of the war, but the story didn't stop in the field. Back at Aberdeen Proving Ground, engineers were watching. They'd been working on the large hatch hull redesign for months, a new glacis configuration that would eliminate the problematic driver's hoods entirely. The small separate plates would be replaced by a single, better angled casting, with large hatches that didn't create seams. The field reports from North Africa and Sicily accelerated the program. If welders in a tent could improve survivability with scrap steel and hand torches, what could a factory do with proper tooling and engineered solutions? The large hatch M4A1 entered production in late 1943. The glacis was now a single cast piece. No hood seams, no weak joints, no shot traps where thin plates met thick ones. The driver and co-driver accessed the tank through large overhead hatches that didn't compromise the frontal armour geometry. By early 1944, the M4A3 variants incorporated the same principles: better armour layout, fewer seams, thicker coverage at critical points. And the cast hull variants, The M4A1 models that had always used one-piece front sections became the preferred design for exactly the reason Harlow had demonstrated in Tunisia. One solid piece of steel is stronger than multiple plates welded together. The lessons from field welding became factory doctrine. Production lines that had been riveting and welding multi-piece hulls shifted toward large castings and single-piece assemblies. The seams that had been killing crews in 1943 were designed out of existence by 1944. Tank crews in Europe noticed the difference. The later production Shermans felt more solid, took hits better, didn't crack at the stress points the way early models had, but thousands of early variant Shermans were still in service, still fighting, still carrying the same vulnerabilities. So the depot welding continued. From North Africa to Italy to France, ordnance crews kept adding applique plates, hood reinforcements, turret cheek plates, sponson armour. The modifications that had started as unauthorized field repairs became routine maintenance procedures. What began as one welder refusing to wait became the standard across 2 theatres of war. Harlow never got a medal, never got promoted beyond Staff Sergeant, never got his name in a report, but he got something better. He got crews walking away from hits that should have killed them. Fewer seams, better shapes, tougher tanks. The war ended in 1945. Ben Harlow went home to Scranton and opened a welding shop on Lackawanna Avenue. He fixed truck frames and repaired factory equipment and never talked much about North Africa. When customers asked if he'd served, he'd nod and say he'd been in ordnance. If they pressed for details, he'd shrug and change the subject. There were no newspaper articles, no ceremony at City Hall, just a welder who went back to welding. But the tanks remembered. By 1944, American tank production had fully absorbed the lessons that started in a forward depot under canvas. The M4A3E8, the Easy 8 Sherman that became the standard late-war variant, incorporated every principle Harlow had proven with scrap steel and a hand torch. Single-piece cast sections eliminated seams. Large hatch glacis removed the driver's hood weak points entirely. Thicker armour at critical zones replaced the thin spots that German gunners had exploited. Better welding specifications across all production models reduced the stress fractures that had plagued early hulls. The philosophy had shifted. Fewer joints, better geometry, stronger at the points where combat proved weakness. And when production couldn't keep pace with the frontline need, when early model Shermans still had to fight in theatres where every tank mattered, the depot welders were there, adding plates, reinforcing seams, buying crews the extra second they needed to survive the hit and return fire. The practice spread beyond Shermans. Tank destroyers received applique armour over their thin hull sides. Half-tracks got reinforced crew compartments. Even some armoured cars were up-armoured using the same techniques Harlow had developed. The US Army Ordnance Department published technical manuals codifying the procedures. Proper bevel angles, preheat temperatures, weld sequencing to minimise distortion, inspection standards. What had been field improvisation became institutional knowledge. Other armies noticed. British tank crews in North Africa started requesting similar modifications. Canadian armoured units adopted applique welding for their Shermans. Even some Soviet tankers, receiving Lend-Lease M4s, added their own field reinforcements based on the American practice. The principle was universal. The people closest to the problem see the solution first, not the engineers in Detroit, not the planners at Aberdeen, the welders in the depot tents, the crews who climbed into tanks knowing exactly where the armour was too thin. They knew because they paid the price when the steel failed. Harlow understood that. He'd watched crews come back with cracked seams, watched them go back out in the same tanks with the same weak points, and he'd made the only choice that made sense. Fix it now. With what you have, make it better than it was. In 1952, 7 years after the war ended, a man walked into Harlow's welding shop in Scranton. He was younger than Harlow, maybe 30. He stood in the doorway for a moment, looking around at the workbenches and the smell of flux and the familiar sound of an arc crackling in the back room. "Help you?" Harlow asked. The man hesitated. "You Ben Harlow? Sergeant Harlow, 3rd Armoured?" Harlow set down his work. "I was a driver," the man said. "Sherman, Tunisia through Sicily." Harlow nodded slowly. "May of 43, our tank took a hit. Right on the driver's hood, same spot that killed the crew before us." The man's voice was quiet, steady. "But we had these plates. Welded on at some depot. The round hit and bounced. I felt it through my seat. But it bounced." He looked at Harlow. "Someone told me you were the one. That you started it." Harlow didn't know what to say. "I got married last year," the man continued. "Got a daughter now. 3 months old." He reached out his hand. "Thank you." Harlow shook it. The man left, and Harlow went back to work. He never told anyone about that conversation, but some nights when the shop was quiet and the acetylene tank sat cool in the corner, he'd think about it. About the crews who came back, about the ones who didn't, about the difference that a bevel and a preheat and a steady hand could make. The bead cools to a dull grey, the slag chips away clean, the metal rings true under the hammer. And somewhere, in a museum, in a depot, in the back corner of a collector's field, a Sherman sits with rough welds still visible on its hull, anonymous, unpolished, holding. Those welds have no signature, no name stamped in the steel, but they're there, and so are the men who walked away because of them. Ben Harlow died in 1967. His obituary in the Scranton Tribune mentioned his welding business and his service in North Africa. It didn't mention Field Service Modification Work Order G104-W57. Didn't mention the survival rates. Didn't mention that his refusal to wait had influenced an entire generation of tank design. It just said he'd been a welder, which was true. He saw a problem. He fixed it. He saved lives. The rest was just steel doing what steel does when someone welds it right. Strong enough to matter. Simple enough to work. Done because it needed doing. One sergeant, one torch, one decision to make the weak line strong, and the tanks kept rolling.